Hello everyone, welcome to Gyanway. So today we are going to start the GATE 2016 solution. So today's agenda is chemical engineering thermodynamics. So the first question which came in thermodynamics subject in GATE 2016 was a liquid mixture of ethanol and water is flowing as inlet stream P into a stream splitter. It is split into two streams Q and R as shown in figure below. The flow rate of P containing 30 mass percent of ethanol is 100 kg per hour. What is the least number of additional specification required to determine the mass, flow rates and composition of the two exit streams? So we are given with this kind of phenomena in which a stream is splitting and the flow rate of P is given, 30% ethanol it contains, and we need to find the mass flow rate of Q and R and the compositions of both of them. So we are asked how many additional specifications we are required in order to find all these values. So how can we find the composition and mass flow rates of Q and R? So first mass balance will be P equal to Q plus R, and the second one will be P into 0.3 equal to Q into X plus R into 1 minus X. So if we know now we already know P which is given as 100 kg per hour, and now we need to find QR and X. If we will have XA, then definitely we can find XB also by XA plus XB equal to 1. So here there are two equations and there are three unknowns, so this cannot be solved. So we should have two equation and two unknown. So definitely we should know only one single specification. We need only one additional specification. If we will get X, then we will have two equation, two unknown. So in this way we can find all other values. So the answer for this question is 1. Now the next question is the partial molar enthalpy is given in this form, in which x1 and x2 are given as mole fraction of 1 and 2, and we are asked infinite dilution of species 1. We are asked the partial molar enthalpy of species 1 at infinite dilution. So infinite dilution means, the word itself says infinite dilution means we are diluting so much, infinite value, so much up to infinite. So means if we are diluting x1, if we are making the solution dilute for species 1, so species 1 will automatically tends to 0 and species 2 will become 1. So here we are given with this thing, this question, h1 equal to 2 minus 60 x2 square plus 100 x1 x2 square. So in this form, if we will keep x1 equal to 0, so this whole term will tends to 0. Now if we will keep x2 equals to 1, so x2 is equals to 1, we will get h1 bar equal to minus 58. So minus 58 is the right answer for this question. So you need to understand this thing only. Infinite dilution of species 1 will be equal to x1 equals to 0, and infinite dilution for species 2 will be x2 equal to 0. So that's it. So the next question came in GATE 2016 for chemical engineering thermodynamics was, there a jacketed stir tank is given with a heat removal provision is used to mix sulfuric acid and water in steady state flow process. So H2SO4 is given at 4 kg per hour, H2O is given as 6 kg per hour at 10 degrees Celsius. So these are the data were given, and it is asked if the mixed stream leaves at 40 degrees Celsius, then what is the rate of heat removal. So the question is that we are adding water plus H2SO4, water and H2SO4. So if we are adding water and H2SO4 and the stream is leaving, that is H2SO4, and that is also 40%. Now the temperature of this stream is 40 degrees Celsius. The temperature of water is 10 degrees Celsius, and temperature of sulfuric acid here is how much? 25 degree Celsius. Now this mixing is occurring at 25 degree Celsius. So here water flow rate is given 6 and H2SO4 flow rate is given as 4. So now we need to find the rate of heat removal. So rate of heat removal will be first water will goes from 10 degree Celsius to 25 degree Celsius. So water will go from 10 degree Celsius to 25 degree Celsius. So heat required will be Q of H will be equal to M is given as 6, M dot is given as 6. Cp will be equal to m dot Cp delta T. So m dot is given as 6, Cp is given for water is 4.2 kilojoule per kg Kelvin, and this is 6 is kg per hour. So mcp delta t is 15. 25 minus 10 equal to 15. So this is for water. Now this is for water. Now the water is reached up to 25 degrees Celsius. So there is heat of mixing, that is minus 650 kilojoule per kg of H2SO4. This is important, per kg of H2SO4. See the unit, per kg of H2SO4. So 650 kilojoule per kg of H2SO4 means if we the total H2SO4 is 4 kg per hour. So here the total heat of mixing will be minus 650 into 4, because this is per kg H2SO4 and H2SO4 is given as 4 kg per hour. So 650 into 4. Now this is heat of mixing. Now the third one will be both H2SO4 and water mixture will go to from 25 degrees Celsius to 40 degrees Celsius, that is 15 degrees Celsius. So M will be total, M will be 4 water is coming, say 4 H2SO4 is coming, 6 water is coming, means outlet will be at 10. So flow rate of out will be 10 into Cp is given as 2.8. So 2.8 delta T will be 15. Now this heat is going inside, it is going in, and this is coming out. So this will be in the form of 650 into 4 minus 10 into 2.8 into 15, and the next will be plus for water it is 6 into 4.2 into 15. So this answer for this question will come as 1802 kilojoule per hour. So 1802 kilojoule per hour is the right answer for this question. The next question is a very interesting question. An ideal gas is given and it is adiabatically and irreversibly compressed from 3 bar 300 Kelvin to 6 bar. Now we are given that work required for the irreversible compression is 1.5 times work required for a reversible compression, means work required for irreversible compression is 1.5 times of work required by reversible compression. So from the initial temperature, same initial temperature and pressure to the same final pressure, the molar this is given, the molar volume is given, R is given, and the temperature we need to find at final stage in the case of irreversible compression. So in case of reversible compression, in case of irreversible compression, in case of irreversible compression, we are given temperature Ti, pressure Pi and T, and we need to find T outlet. In reversible compression, Ti is given, Pi is given, and T is given. So in this way, what we can find, how we can find the T2, how we can find T2, T1 P1 is given, T2 P2. Now how we can find P2 is Tp1 minus gamma upon gamma equal to constant. So T1 P1 1 minus gamma, T2 P2 1 minus gamma upon gamma. So this will come as 300 into 3 by 6. 1 minus gamma is given. How much gamma is given? 1.277 upon 1.277. So this is equal to T2. So T2, if you will solve this equation, T2 will come out as 348.67. So T2 came out as 348.67. Now work done by reversible compression is equal to 1.5 times of work done by irreversible compression is equal to 1.5 times of work done by reversible compression. So work done by irreversible compression will be equal to mCp. Again we can take as mCp delta T for irreversible compression equal to mCp delta T for reversible compression into 1.5 times. So here m is 1, m and m will get cut, and cp will get cut. So delta t for irreversible compression. So irreversible compression means T2 final minus T1 is equal to 300 equal to 1.5 times of 348.67 minus 300. I will write it again here. T2 minus 300 equal to 1.5 times of 348.67 minus 300. So here if you will solve this equation, you will get T2 equal to 373.01. So this is the right answer for this question. Now the next question is quite conceptual. In this question, the Clausius equation of state is given, and it is isothermally compressed from 5 megapascal to 15 megapascal at 400 degrees Celsius. So Clausius equation of state is this one, and we are given the parameter B is this for this Clausius equation of state. So B0 is given, B1 is given. Now the effect of pressure on molar enthalpy is given by this equation, and we need to find HF minus HI. So HF minus HI means this del H. Now HF minus HI can be found by this del H. So this del H we need to find. So for this, what we are given with this Clausius equation of state. So Clausius equation of state is given as P equal to RT upon V minus BT. So if we will solve this equation, then PV equal to, by cross multiplication, PV minus BT into P equal to RT. So V will be equal to RT upon P plus B of T, and B of T is given as B0 plus B1T. Now V equal to, we can substitute this thing, RT upon P plus B0 plus B1T. So we got V. Now we got V. Now we need to find del V upon del T. Del V upon del T, and we can integrate with del P. We will get it del H. Now del V upon del T will be equal to, del V upon del T will be equal to R by P see this R by P plus B naught is constant, it will be equal to 0, then B1. Now we can substitute this V value, this, and also this value in this particular equation. So del H upon del P will be equal to, V is equal to RT upon P plus B naught minus B1T minus T into, now del V upon del T at constant P will be equal to R by P plus B1. So this RT by P and RT by P will be cancelled. B1T and B1T will be cancelled again, and then at the end we will left with only B naught. So we are left with B naught, this is plus, so we are left with B naught. So del H upon del P equal to B naught, and B naught value is given as 4 into 10 raised to power minus 5. So we can integrate it. So on integration we will get HF minus HI equal to B naught into delta P. So B naught is 4 into 10 raised to power minus 5 into delta P. So delta P is given as 15 is final, minus 5 megapascal is given. So megapascal, if we will convert into pascal, that is 10 raised to power 6. So 10 into 10 raised to power 6. So this will come out as 4 into 10 raised to power minus 4 into 10 raised to power 6 equal to 400. So 400 joule per mole. So this is the final answer for this question. Now the next question is, we are given with species 1 and species 2, and Margulis equation is given as GE upon RT equal to 3x1x2. GE is, we know that it is molar excess gas free energy, and G1 upon RT value is given, G2 upon RT value is given, and we need to find for binary mixture at 40 mole percent of species 1 the value of G upon RT. So this question was conceptual and but easy question. So G upon RT we know that is equal to G1 upon RT plus G2 upon RT, G1 x1 upon RT plus G2 x2 upon RT plus GE upon RT. So G1 upon RT is 1 into x1 is 0.4 plus G2 is given as 2, x2 will be 1 minus 0.4, 1 minus 0.4 will be equal to x2. So this is equal to 0.6 plus GE upon RT. So GE upon RT is given as 3x1 x2, 3x1 x2. So this is 0.4 plus 1.2 equal to plus 3 into 0.4 into 0.6, 6 into 0.6 into 0.4, 24. This is equal to 0.72 plus 1.2 plus 0.4. So this will be equal to 2.32. So this is the final answer for this question. Now the next question is given as a catalytic reforming plant produces hydrogen and benzene from cyclohexane. So cyclohexane is C6H12. C6H12 gives H2 plus C6H6. This is given in the question. C6H12 gives H2 plus C6H6. In order to increase the production of hydrogen, what the owner did was he introduced steam reforming process which produces hydrogen and carbon dioxide. So steam reforming process, with the name we can say he is giving that the owner is giving steam with C6H12. So C6H12 plus steam, that will be equal to H2O, and it will give hydrogen plus carbon dioxide. Now we need to find the maximum ratio of pure hydrogen produced in the proposed process to that of existing process. So this is the existing process and this is the proposed process. So we will balance this equation by, we know that C6H12 gives H2 plus C6H6. So here there are 6C. Now here are 12 hydrogen, here 6 hydrogen, so we need more, 6 hydrogen more, so 3 into H2, this is 6 plus 6 equal to 12. So now this equation is balanced. Now this reaction, in this reaction C6, so this will be 6 carbon. Now oxygen became 12 here, so here there will be 12 oxygen, so 12 oxygen. Now here hydrogen is 12 into 2, 24, 24 plus 12, 36. So this is 2, so means here will be 18. Now here 18 hydrogen is producing, so 18 hydrogen in proposed reaction divided by 3 hydrogen in existing reaction, which will be equal to 6. So answer for this question is 6. So that's it for thermodynamics part of GATE 2016. For more such video, you can always subscribe our channel. Thank you very much. And if you have any doubt, you can post a comment or you can ask in our Facebook group. Thank you very much.